trying all the possible ways to assign variables, we may check whether a formula is true. This strategy is exponential in the number of variables. It does not scale to other logical systems, like first-order logic. It does not show why the formula holds. Thus, we want a notion of proof. We say that a theory is a set of formulae, each one called axiom. A proof is an expression constructed from a set of formulae called assumptions, aimed toward a formula called the conclusion. We are allowed to use the axioms of a prefixed theory. The conclusion of a proof with no assumptions is called theorem. The syntax of proofs is described in the following. We write the syntax using inference rules. The conclusion is below the line and above are the premises, which have to be proofs even if only their conclusions are written. The order of the premises is irrelevant. On the side of the line, we write the inference rule in use. To deal with conjunction, we have an introduction rule and two elimination rules. There are three rules governing disjunction. The two introduction rules are quite obvious. The elimination rule is more complex. We deduce C by an elimination from a proof of A or B and a proof of C from A and a proof of C from B. The rationale is that 1 in AB is true, so either the second or the third premise can be used to deduce the truth of C. We use the dots to indicate a proof and we write the additional assumptions above. The assumptions in square brackets indicate that these assumptions are local to the second and the third premise, respectively, but they are not assumptions of the whole proof. We refer to them as discharged, and we say that an elimination discharges them. The rules for implication are similar. To deduce A implies B, we have to prove B from the assumption A, and the final proof does not depend on the assumption we make. If we know A implies B and A, we can deduce B. Negation is very similar. Introduction means that we are able to prove falsity assuming A, and elimination means that whenever we are able to prove not A and A, we can deduce falsity. We can always introduce true, and we can deduce whatever we like from falsity. If A is an axiom in the theory we are using, we can always deduce it. If A is an assumption, we can deduce it. We write assumptions without indicating the rule which introduced them. This is not a problem, since they are the leaves of a proof tree. The law of excluded middle is given as an axiom for every formula A. We prefer to avoid it whenever possible, for reasons that will become apparent much later in the course. Most rules come in pairs, introduction and elimination. Assumptions are free when introduced by the assumption rule. Assumptions are also introduced by or elimination, implies introduction and not introduction. These assumptions can be, and usually are, discharged, but discharging is optional. Discharged assumptions are local to the subproof to which they refer. They can be used there and not elsewhere. However, the whole proof doesn't depend on discharged assumptions. We introduce some notation to indicate implicit proofs. They are detailed in the bottom of the slide.